Continuation. Natural resources and their assessment. Natural resources and their assessment. Natural resources are the fundamental building blocks of human civilization, providing essential materials and energy for economic and societal development. They encompass a wide range of elements and features in the environment that are utilized for various purposes. Assessing natural resources is crucial for sustainable management, conservation, and equitable distribution. So, types of natural resources. Renewable resources. Renewable resources can be replenished naturally over time and are considered sustainable. Examples include sunlight, wind, biomass, and water. Non-renewable resources. Non-renewable resources are finite and will be exhausted over time with continued use. Examples include fossil fuels, coal, oil, natural gas, minerals, and nuclear fuels. And biotic resources. Biotic resources are derived from living organisms and include forests, fisheries, and agricultural crops. Sustainable management is crucial to prevent depletion. And abiotic resources. Abiotic resources are non-living components of the environment such as material, minerals, rocks, and water. They often require extraction and processing. Assessment of natural resources. Assessing natural resources involve evaluating their quantity, quality, distribution, and sustainable use. This assessment is vital for informed decision making, conservation efforts, and resource planning. Resource inventory, gathering comprehensive data on presence and location of natural resources, utilizes techniques like geological surveys, aerial mapping, and remote sensing. Resource quantification, measuring the quantity and volume of available resource. Examples include estimating oil reserves in barrels or mineral deposits in tons. And resource quantity assessment, evaluating the quality assessment, evaluating the quality, purity, and suitability of resources for specific applications. Quality control is essential for industrial like agriculture and mining. Then distribution analysis, studying the geographical distribution of resources to identify areas of abundance or scarcity, helps in equitable resource management and allocation. Then economic valuation, determining the economic value of natural resources considering both direct and indirect benefits, includes ecosystem services like clean air, water purification, and pollination. Sustainability assessment, evaluating whether resource extraction and utilization can be maintained without depleting future availability, involves assessing environmental impacts and regeneration rates, challenges in natural resource assessment. Data availability, limited and outdated data can hinder accurate assessments. Then complexity, assessing complex ecosystems and interrelated resources can be challenging. Then conflicting interests, balancing economic development with conservation goals and competing interests. Environmental impact, resource extraction often has negative ecological and environmental consequences. Then importance of assessment, sustainable management. Effective resource assessment is crucial for sustainable management and conservation, preventing overexploitation and depletion. Then policy formulation, data from assessments informs policy decisions such as land use planning and conservation strategies. Then economic planning, resource assessments are fundamental for economic planning, industrial development, and infrastructure projects. Then environmental protection, protecting vital ecosystems and preserving biodiversity depends on accurate resource assessments. In conclusion, natural resource assessment is a multidisciplinary endeavor that combines specific scientific data, technological tools, and policy considerations to inform decision making and ensure the sustainable utilization of resources. So, understanding the types of natural resources, the methods of assessment, and the challenges involved is essential for scholars and professionals working in fields related to environmental science, geography, economics, and sustainable development. Then, remote sensing and GIS. Remote Sensing and Geographic Information Systems, or GIS. Remote sensing and geographic information systems are powerful tools used to collect, analyze, and visualize spatial data, making them invaluable in various fields including environmental science, geography, urban planning, disaster management, and agriculture. These technologies have revolutionized the way we study and manage Earth's resources and landscape. Remote sensing definition and principles. Remote sensing refers to the process of acquiring information about the Earth's surface without direct physical contact. It involves the use of sensors and instruments on satellites, aircrafts, or ground based platforms to collect data from a distance. In electromagnetic radiation, remote sensing relies on the interaction between electromagnetic radiation, visible infrared, microwave, and the Earth's surface. Different materials reflect, absorb, or transmit radiation differently, allowing for the identification of features. And types of remote sensing. Passive remote sensing. Passive sensors detect natural radiation emitted or reflected by objects on Earth's surface. Examples include optical sensors, visible and infrared and thermal sensors. Active remote sensing. Active sensors emit their own energy, radar or lidar, and measure the return signal. These sensors are useful for capturing data even in adverse weather conditions or at night. So, applications environmental monitoring. Remote sensing is used to monitor land use changes, deforestation, urban growth, and habitat mapping. Agriculture, it aids in crop health assessment, soil moisture estimation, and yield prediction. Then disaster management. Remote sensing assists in disaster management such as flood monitoring, wildlife detection, and wildfire detection, and post-disaster damage assessment. Then meteorology, weather forecasting relies on remote sensing data for monitoring atmospheric conditions. Then remote sensing platforms, satellite remote sensing provide global coverage and long-term data archives. So examples include NASA's Landsat and the European Space Agency's Sentinel missions. Aircraft. Aerial imagery is collected by aircraft, often at higher spatial resolutions than satellites. Then drones and unmanned aerial vehicles, UAVs, or drones offer flexibility and are used for localized high resolution data collection. So, geographical information systems or GIS definition and principle. GIS is a computer based system that captures, stores, analyzes, and displays geospatial data. It allows users to visualize and interpret data in the context of maps and spatial relationships. So, spatial data, GIS relies on spatial data, which includes information about the location, shape, and attributes of features on Earth's surface. So, components of GIS databases contain spatial data, geometric shapes, and attribute data, descriptive information. Software, GIS software allows users to input, manage, analyze, and visualize spatial data. Then hardware, computers, GIS devices, and other hardwares are essential for GIS operations. People, GIS professionals, collect, analyze, and interpret data, making informed decisions. So applications, urban planning, GIS aids and land use planning, infrastructure management, and transportation planning. And natural resource management, it is used for forest inventory, water resource management, and wildlife habitat analysis. Then healthcare, GIS helps in disease mapping, healthcare facility, along with location planning and epidemiological studies. Emergency management, GIS supports disaster response, evacuation planning, and risk assessment. Then spatial analysis, GIS allows for complex spatial analysis including overlaying multiple layers of data, proximity analysis, network analysis, and modeling. Remote sensing and GIS integration. Remote sensing data can be integrated into GIS to provide updated and accurate spatial information for decision making. So, combining remote sensor imagery with GIS allows for applications like land cover classification, change detection, and environmental modeling. So, in conclusion, remote sensing and GIS are essential tools for acquiring, managing, analyzing, and visualizing spatial data. They play a pivotal role in diverse fields, helping professionals make informed decisions and address complex spatial challenges. Then, principles of remote sensing. Remote sensing is a science of capturing information about the Earth's surface from a distance using sensors and instruments in various platforms such as satellites, aircraft, and drones. It relies on several fundamental principles like electromagnetic radiation interaction. Remote sensing is based on the interaction between electromagnetic radiation and the Earth's surface. Electromagnetic radiation includes various wavelengths, from radio waves to gamma waves. Different materials on Earth's surface interact with EMR in unique ways. For example, vegetation reflects near infrared radiation strongly while water absorbs it. Then spectral signatures. Each material or substance has a characteristic spectral signature which represent how it reflects, absorbs or emits radiation at different wavelengths. Spectral signatures are used to identify and differentiate materials on the Earth's surface and remote sensing imagery. Then sensor characteristics. Remote sensing sensors are designed to capture specific ranges of EMR wavelengths. For example, optical sensors capture visible and infrared wavelengths, while radar sensors operate in the microwave range. So, sensor characteristics including spatial resolution, spectral resolution, wavelength discrimination, and radiometric resolution. That means sensitivity to brightness, impact the quality of remote sensing data. So, platforms and orbits. Remote sensing data can be collected from satellites in various orbits like polar, geostationary to form from aircraft. The choice of platform affects the revisit time and spatial coverage. So, geostationary satellites provide continuous monitoring of a specific region, while polar orbiting satellites cover the entire Earth's surface over time. Then, image interpretation. Image interpretation involves visual or digital analysis of remote sensing imagery to identify and classify features on the Earth's surface. And interpretation relies on knowledge of spectral signatures, spatial patterns, and contextual information. Contextual information. Then temporal resolution. Temporal resolution refers to the frequency at which data is collected over the same media. Frequent revisits are essential for monitoring dynamic changes such as vegetation growth or urban expansion. Then principles of geographic information systems or GIS. GIS is technology that integrates spatial data, geospatial information with attribute data and non-spatial information to create meaningful maps, analyze spatial relationships, and support decision making. Its principles include spatial data monitoring. GIS models Earth's surface as a series of layers or maps, each representing specific geographic features or phenomena. Then spatial data models include vector data, points, lines, polygons, and raster data. Gridded cells. So data integration. GIS combines different types of data, including spatial or non-spatial data, into a single geospatial database. Spatial data is linked to attribute data through a common identifier such as a geographic coordinate. Then georeferencing. Georeferencing assigns geographic coordinates, latitude and longitude, to spatial features, allowing them to be accurately positioned on the Earth's surface. It ensures that spatial data aligns correctly with other data layers. So, spatial analysis. GIS enables various spatial analysis such as proximity analysis, meaning distances and nearest neighbors. Then overlay analysis, combining layers to identify intersections, and spatial modeling, predicting spatial patterns. Then cartographic output. GIS produces maps and visualizations to communicate spatial information effectively. So, cartographic principles such as map scale, symbols, and labeling are important in map design. Data query and retrieval. Users can query GIS databases to retrieve specific spatial information based on attributes or spatial relationships. Query results can be used for decision making and analysis. Database management. GIS databases require efficient management, including data storage, indexing, and maintenance to ensure data integrity and accessibility. So, metadata provide essential information about the sources, quality, and content of geospatial data, facilitating data sharing and understanding. Then interoperability. GIS systems often need to work with other software and data formats. So, interoperability standards ensure compatibility and data exchange between different systems. Privacy and security. GIS data often contains sensitive information, so ensuring privacy and data security is crucial in GIS applications, especially in public administration and healthcare. So, integration of remote sensing and GIS. Remote sensing and GIS are often used together to combine the spatial information captured by remote sensing with the analytical capabilities of GIS. This integration allows for applications like classification, land cover classification, change detection, and environmental monitoring. Next topic we will be learning with the help of next video. So in conclusion, remote sensing and GIS are essential technologies for capturing, managing, analyzing, and visualizing geospatial data.